So Newton's universal law of gravitation. So this was Newton realized, he did all, Newton did a lot of theories. He's got his 3 laws of motion, but also he's very famous for his theory of gravity. Okay, so he suggested that everything with a mass exerts a force on anything else with a mass. Okay, and however, the bigger the mass, the bigger the force. Okay. He also suggested that obviously the further away something is, the less the force is going to be felt, which makes sense, doesn't it? Okay. So, although early astronomers such as Kepler had made observations of the motion of planets and had even predictions about them and formulated equations describing their motion, it wasn't until Isaac Newton published his great work, the Principia, that anyone suggested a reason why stars and planets behave as they do. If anyone wants to borrow a Latin version, I lent to Becca once, of the Principia, feel free. If you'd ought to be able to understand if you understand Latin, though. Because back in those days, everybody wrote in Latin. So all the scientific books were in Latin. Newton suggested that the mass of an object exerts a force of attraction on all other masses in the universe. This force of attraction is directly proportional to the product of the 2 masses and inversely proportional to the square of the distance between them. So Newton considered all masses to be point masses. That means when we're applying his laws, we consider the object as if all mass is concentrated in the very centre of the object. And you'll find this even if you go on and do physics at university, we tend to estimate things being point masses. Okay, so they're just all the mass is right in the centre. We know that's not true. We know that the Earth isn't a perfect sphere. We know that things like that don't actually occur, but it's a good estimation. So this is obviously an approximation, but as long as you are sufficiently far away from an object under consideration, it works. So it works with planets, it works with the solar system, things like that. So mathematically, Newton's law of gravitation is written as force is proportional to the mass of one thing times by the mass of the other thing, divided by the distance between them squared. So where F is the force of attraction between 2 masses, M1 and M2 are the 2 masses being considered, and R is the distance between the centres of mass of the 2 masses. Now it's important that it's the distance between the centres of mass. So if you're looking at the Earth and the Sun, you have to take into account the radius of the Earth as well, because if you've got 2 things, 1, 2, you may be given that distance there, but you'd also need to take into account the distance into the centre of the bodies as well. Okay, so just be careful with questions like that. So if we want to make this into an equation, we introduce a constant of proportionality. We give it the symbol capital G, not to be confused with lowercase g. So force is capital G, so that's a gravitational constant, times by mass 1 times by mass 2 divided by r squared, which is the distance between the centre of masses. And the size of the constant is determined by the units of measurement. It was not measured accurately until well after Newton's death by a scientist called Henry Cavendish, due to the fact the size of the force generated between masses in the lab is very small, very difficult to measure. Henry Cavendish I think he did it in Scotland. He was measuring the force of attraction between a mountain and a really small sort of pendulum kind of thing. And he actually used a mountain to help him measure it. So G is, and you'll be given this obviously, but it's 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. So example 5, calculate the force of gravitational attraction that exists between 2 pupils, one of mass 55 kilograms, one of 70 kilograms, when they're sitting a distance of 0.85 meters apart. Okay, there will be a force, but it will be very small. So, because obviously you guys aren't getting, sucked into each other. So F equals G, sorry, I missed out the G. G M1 M2 over R squared. So 6.67 times 10 to the minus 11 times by 55 times by 70, and we're assuming that that distance, because we're not given the radius of the person, and people don't really have radiuses, and we're assuming that is the distance 0.85 squared. Remember to do the squaring. And that should come to 3.55 times 10 to the minus 7 newtons, so really small. But there is a force there. But obviously, forces between two pupils is not going to be very big at all. Okay. But very small when it says comment. Okay, so example 6. A person of mass 75 kilograms sits on the surface of the Earth. Data for the Earth is given below, so we're given the mass and the radius. So if you're given the radius of the Earth, you probably need to use it. Calculate the gravitational attraction between the person and the Earth. So basically what's happening is we've got a person on the Earth, sitting on the Earth. So the distance between the centre of mass of the Earth and the person is going to be the radius of the Earth. So the gravitational force of attraction, F equals G m1 m2 over r squared. So G 6.67 times 10 to the minus 11 times by mass of the Earth, which is 6 times 10 to the 24, times by mass of the person, who's 75 kilograms, divided by the distance between them is the radius of the Earth squared. So 6.4 times 10 to the 6 squared. Another thing to be aware of is quite often these big numbers are given in kilometres rather than metres. You need to change it to metres quite often. But you don't need to this time. So that should come to 733 newtons. Okay, so again, you just need to make sure you're putting everything into your calculator properly as well, because we know from the other day there are a lot of things we can forget to do, and we can end up putting things in wrong in the calculator. Part B, I'm sure you guys can do that yourself. Calculate the weight of a person by traditional means. So W equals mg. So hopefully you will come to the conclusion that they are pretty much the same. Okay, slightly different, but we can say that they are almost the same. I remember, if you can remember back to first year when we used to draw in, see that the mass and weight are different. Mass is the amount of stuff that's in you, and weight is the force due to gravity, force pulling you down to the centre of the Earth. That is the force of attraction of the Earth on a body. Okay, so there's two ways that you can work out the weight. You can either work out W equals mg, or you can work out the force of attraction between the person and the Earth. So you can work out your weight if you know your mass by doing a very complicated equation, or obviously the simple one. Okay, so just to state that on the next page, weight and gravitation. So the reason why there is a force called weight pulling you down is because there is a gravitational attraction between you and the Earth, since both of you have masses. So the weight is the force of gravitational attraction. So we can form an equation for our own weight using W equals mg. And we know that the gravitational attraction is g m1 m2 over r squared. So we can say that, because we know that weight equals force, so mg equals g m1 m2 over r squared. And that's what that equation here is showing you. So mass of the person times by the gravitational field strength is equal to gravitational constant times by the mass of the earth times by the mass of the person divided by the radius of the earth squared. And seeing as the mass of the person is the same on both sides, cancel this out, and you can work out what the gravitational field strength is if you know the mass of the earth and the radius of the earth. So you've got another equation there. Gravitational field strength is the gravitational constant times by the mass of, in this case, the earth, divided by the radius, in this case, the earth squared. You can do the same for any planet. So you can find gravitational field strength for any planet by gravitational constant times by the mass of the planet, or the moon, or whatever, divided by the radius of the planet squared. So we can measure G on the like lowercase g, gravitational field strength, on the surface of the Earth. Uppercase G, the gravitational constant, is a known constant, known because of Henry Cavendish. The radius of the Earth is a little trickier, but it can be determined by considering the curvature of the surface of the Earth to be the arc of a circle. This equation can then be used to establish a value for the mass of the Earth itself. And how else could G be measured? Well, you could drop a ball, and you could use a meter stick and a stopwatch, release the ball from fixed height, starting from rest, time how long it takes to hit the ground, and then use an equation of motion to determine the value for the acceleration due to gravity. Why might this not be quite so straightforward if you're just dropping a ball? Get our... Sorry? Yep. Human error? Air resistance? Yeah. So air resistance, human error. Yeah. Lots of different errors that you can get in that. So that's what I was going to do tomorrow. I'm going to get, as I said, it's 2 halves of the lesson, one half with fewer people in. But first, when we've got fewer people in, you guys are going to do the planning. You're going to get on the internet, find some different ways to measure G, more accurate than that, hopefully. And then in the afternoon, those of you that are not in the morning can come in and perform the experiment and write it up like you would write up an assignment. Okay. Right, but for now, what I'd like to do is do some questions based on these two equations. So question booklet, page 11 of your question booklets, and then there are some past paper, there's some worksheets at the front in front of Becca as well if you finish those. Yep, page 11 of your question booklet. No.